Hello, everybody, and welcome to another episode of the Extreme Performance Series. I'm Todd Muirhead, and today I have with me Qasim. Qasim, could you go ahead and introduce yourself real quick?
My name is Qasim Ali, and I'm a distinguished engineer in the VCF Performance Engineering team. For the past 15 plus years, I've been working on optimizing the performance of ESX resource management stack, for example, CPU and memory scheduler and power. I've been always interested in optimizing the ESX hypervisor for latest processors and memory technologies. And talking about memory technologies, these days I am the performance lead for the memory tiering projects at VMware by Broadcom.
Yeah, and I've gotten to work with you some on the mem tiering stuff, and so I'm really excited to get to talk about it with everybody today. So, what do you have to share with us today?
Today, I'm going to talk about how memory tiering technology can improve server consolidation and overall optimize the total cost of ownership of your server infrastructure. So, memory tiering is implemented in the ESX kernel by optimizing the memory scheduler, and it's transparent to the applications and the guest operating systems. So for example, this is how the logical view is to the end user. You still have your VM, you have your DRAM, you go to the settings and allocate this much memory to your VM. You don't need to worry about where that particular memory is coming from. Behind the scenes, ESX divides that memory into two tiers, tier 1 and tier 2. Tier 1 memory being DRAM, which is a faster memory, Tier 2 being cheaper and bigger memory, and that's typically slower devices like NVMe SSDs and CXL memory devices. Today, I'm going to focus on advanced memory tiering using NVMe SSDs that was announced as part of VCF 9 at the VMware Explore at Las Vegas. So how this works is vSphere decides what tier to use and when to use them. So the overall memory which is available to your end user will be the summation of all tiers, in this case, DRAM and NVMe. So in this case, I have a vSAN cluster with 6 hosts. And if you look at one of the hosts, you click on the overview, you go to the overview, hardware, and then you look at the memory screen. So in this case, I have configured it to use 1:1 DRAM to NVMe ratio. What this means is that for every gigabyte of DRAM, you get 1 gigabyte of NVMe. That's what is 1:1 NVMe ratio. As you can see here, your total system available memory is 1 terabyte, and 512 gigabytes is coming from DRAM, which is a faster tier, and 512 is coming from your NVMe tier, which is unmappable memory.
So, Qasim, this looks a lot like the stuff that we've had in the past, the memory overcommitment or the ballooning stuff that we've had in the product for a long time. How is this different?
So let me dive a little bit deeper on how we implemented this feature. Now let's look at this host. Let's say this has two VMs, and obviously we are using two tiers, so the memory pages will be divided into two tiers. Now we have a very intelligent page classification scheme that is completely new. It figures out which memory pages they are hot and which of the memory pages are cold in a specific time window. For example, in the past 1 minute or so, how many pages are accessed more frequently. So the most frequently accessed pages within a given time period will be classified as hot pages. And obviously you want hot pages to go into a faster tier, which is DRAM, and the colder pages will go on the slow tier. So that's one difference. Once the VMs are running, you could see that in your typical environments, the workload characteristics would change. So we continue monitoring that and keep on changing this classification, and it keeps on running in a feedback loop. So your system is going through phase changes, you're running database transactions, sometimes you're not running anything. So this system will automatically adjust all these tier sizes so you can really optimize your memory usage. So that's number one. Now, number two, you talked about ballooning. So what we have seen is that ballooning in certain cases like large databases, Oracle or SQL Server, you're running these databases and you're using large pages. And these large pages are locked by the guest operating system. Now, what Balloon Driver does is it requests the guest OS to get some memory out of the VM. These pages are locked, and this Balloon Driver is trying to get these pages, but obviously your database is not going to give them up. So you run into these issues where Balloon Driver is trying to request this, and then the guest OS not giving up, and you are burning a lot of CPU cycles, and you run into all sorts of these performance issues. In this one, you don't have to worry about it. Whatever memory available you have, you just use it with confidence. You will not see ballooning. You will not see host swapping. And the key differentiator here is we have intelligent host swapping based on the hotness. In the previous one, it was all random. So that is the key differentiator. Now let's see what is the main underlying assumption, how this solution will work in the field and how we can actually improve the server consolidation. We have a very interesting customer called SS&C Cloud. They are in the financial and healthcare sector. So what they have is a big fleet of servers and they are running all sorts of workloads. They are running databases, SQL Server, Oracle, VDI workloads, container workloads, Linux VMs, Windows VM, they have it all. So across their fleet of these workloads and servers, they have this analysis, which is your consumed memory is roughly 1 petabyte, right? 861 terabytes. What is consumed memory? Consumed memory is whatever memory is allocated and granted and minus the memory you save from the page sharing. That is consumed memory. What they observed is that the active memory, which is the portion of the memory that is frequently accessed, is just a fraction of that total memory, which is only 9%, right? So that's pretty low. And why that's a concern? Well, the total cost of the DRAM is 50 to 80% of the cost of the server. Now, if all this memory is sitting idle, you're spending all this money but not really using it. Why does this happen? These applications, they are more memory capacity bound. So you're hitting that memory capacity and you're not able to allocate more memory. So what do? We unlock this additional memory using NVMe as the second tier. Now, if you look at their just average VM sizes and average host sizes and what's their consumption and activeness looks like, and again, their activeness is pretty low. Now let's look at the core angle. Most of your application licenses like SQL Server licenses or your hypervisor licenses are based on the number of cores. Now, if you look at this trend, your servers continue to get denser in terms of cores exponentially. Memory is going up too, but not exponentially. If your applications are memory bound, you will hit this memory capacity first and you leave some of the cores which are idle. So again, NVMe memory tiering will unlock these cores. It will unlock this additional capacity using NVMe as the secondary device, which is a cheaper device. Our friends at SS&C have done this math for us and they believe that tiering can reduce the memory cost by up to 50%. That's a huge number. All right, now that I have sold you how memory tiering can optimize your VM density, let's go into the performance results. And for this one, we used the NVMe as a tier device with 1:1 DRAM to NVMe ratio. That means, let's say we have a 1 terabyte of DRAM host, you use an additional 1 terabyte of NVMe capacity to increase your system memory. Now, the workloads which we have chosen are ranging from smaller VMs, a lot of VMs like VDI. We have used SQL Server, which is a big workload which is deployed by our customers. And then finally, Oracle workload. As you can see, have played with different vCPU sizes, memory sizes to get a good sense of how our solution is working out. And for VDI, I have used an industry standard benchmark called Login Enterprise. For this chart, if you look at the y-axis, I have on the left-hand side the number of VMs. On the right-hand side, I have the EUX score. This is called End User Experience Score. So they do a variety of operations like running Microsoft Excel, opening PowerPoint, running a video, just like a typical VDI user would do. And then they combine all these latencies into an end user experience score calculated based on latencies. According to the Login Enterprise guidelines, any score above 8 is an excellent score. So 6 to 8 is a good score. On the x-axis, I have the capacity first showing DRAM, which is 1 terabyte. And then memory tiering as it's unlocking the additional NVMe capacity tier. So we have 2 terabytes. Now the first result is the baseline, which is only using DRAM 1 terabyte of memory. So you get an end user score of about 8.5, which is an excellent score. Now if we enable memory tiering, you can run twice as many VMs. So you were able to run 120 VMs in the baseline. And when you enable memory tiering, you can run 240 VMs. The end user score is not degraded. As you can see, it's more or less the same. And this result has been validated by log and VSI. So overall, the message is that you get 2x increase in VM density with less than 3% performance loss.
So, Kasim, with these results, this is great to see the user experience is basically staying the same. But is there any overhead for the memory tiering that's going on in the background to enable this much larger number of VMs running?
I have quantified the CPU overhead, and obviously you're bringing in pages from the NVMe tier device, and then you're trying to put some pages, cold pages onto the device. So this involves some CPU activity. So what I have seen in the worst case, about 10% or so CPU overhead, but I'm not worried about it. You have a lot of cores left on the table. So using, let's say, 10 cores out of 100, and again, worst case scenario, you could use 10% CPU overhead. Across a wide variety of benchmarks, I have seen the CPU overhead hovering more or less 3 to 5%. So let me now talk about my next result, which is SQL Server using HammerDB. HammerDB is also an industry standard benchmark to test databases. For example, in this case, I have tested SQL Server. My chart looks the same. On the y-axis, I have the number of VMs. On the x-axis, I have the capacity. And then on the secondary y-axis on the right-hand side, I have the throughput. So for the baseline case, I see about 6.2 million transactions per minute. And once you enable memory tiering, you are able to almost get a linear scaling, which is 10.7 million. So overall, you see 2x increase in VM density in this case as well, with less than 10% performance loss. How do I measure this 10% performance loss? So if you look at this brown bar, memory tiering 1 terabyte config, this means you have 512 gigabyte of DRAM and 512 gigabyte of NVMe. Now I have configured an equivalent system using just 1 terabyte of all DRAM. So in this case, your transactions come out to be around 11.8 or 9. So that percentage difference is around 9 to 10%. So once I finished that, I basically started to think maybe I'm biased in this. So I turned to you, Todd, which you are our in-house database expert, right? So can you tell me what did you see with your testing?
Yeah, so I think you're going to put the results up here in just a second. It's very similar. Yeah, so like I said, I get to do a little bit of work on this one with the Oracle database. These VMs are larger than the ones that Qasim used for SQL Server. It's also running on Linux instead of Windows Server. So there's some differences there. We wanted to get a different workload here. So in the base case here, which in this case it was 1 terabyte of DRAM on the host. I was able to run 4 VMs. Like I said, these are much bigger and achieved a throughput of 13,900. This is orders per minute. And then once we enable mem tiering and have now 2 terabytes, we're able to double the number of VMs. We saw performance scale almost linear from where we were. So 2x increase in VMs with a very small performance loss in terms of orders per minute or the throughput of the databases in this case. So, very similar to the other workloads in terms of the net result that we saw, and which is a good proof point for mem tiering on yet another workload.
All right. Now let's look at how to monitor your memory tiering infrastructure. What do I mean by that? You have selected a particular NVMe device as your tier device. And what you would do is you would go to vCenter, you would go to the advanced settings, and you go to a storage adapter that is tied to your tier device, in this case, VMHBF4. And you can monitor the read and write traffic of this tier device. For example, in this case, the reads per second is around 200 and then writes are higher. Now, one thing to keep in mind is that what sort of NVMEs you're using. For example, in our experiments, we were using P5600, P5620s. What are the specs for these? Now, the thing to look for in the specs is random reads. Whenever you get a page fault, and if your page is on the NVMe, it is fetched into the memory through a page fault mechanism. And these page faults are 4K random reads. Now, the specs for these NVMEs say you can go well beyond 1 gigabytes per second for random reads, 1 to 2. So as long as you're below that threshold, you know that you're not really saturating your tier device, right? That's your first thing to look for. For all the workloads which we have tested, Todd, what I have seen is across the board, VDI, SQL, or your Oracle VMs, I have seen that read traffic hovering around 50 to 150 megabytes per second. So that's pretty good. Obviously, one thing is throughput. You have to look at the latencies of these transactions. Now, in order to do that, you can plot those latency characteristics onto the same chart. Now, a rough guideline around these latencies is that as long as your read latencies is below 200 milliseconds, you're all good. If your write latency is below this number, you're good. For the workloads which we have tested, my read and write latencies, they are, below these numbers, Todd.
Yeah, so I just want to caution everybody about these numbers that we're talking about. These are what we saw when we were running our applications and we achieved good performance. You could very well still have good performance with higher numbers with different workloads. If performance is good and then you go in and look at these numbers like we're showing you here and you see that they're higher, don't panic. Your performance is still good. Your numbers just happen to be a little bit higher.
So after looking at these host level stats, let's look into per VM stats. Let's say you have 100 of VMs running, database running around. You would like to see maybe one of your VMs is not performing well. You would like to see how much tearing is happening, how much it's faulting from the NVMe SSDs, right? So you go to a particular VM, and again, you go to the advanced and you go to the memory option, and you can select your NVMe read and write bandwidth. So over here, it will tell you how much of your TA traffic is going. Similarly, you can plot the latencies aspects of it. So this is a very good troubleshooting performance screen that you can look at, Todd. Now, coming to the most important metric around memory, we are talking about memory tiering, right? How do we monitor the memory consumption and your memory activeness? So you go to your host and you select the advanced, and again, you go to the memory screen. Here you can plot your memory activeness. The first top line is memory consumed. Like I said, it is granted memory minus the memory you save from page sharing. And then you look at your active memory, which is the memory which is most frequently used. This is screenshot taken from a system that had a 2 terabyte of total system memory, 1 terabyte coming from the host DRAM and 1 terabyte coming from the NVMe. As you can see, your consumed memory is going up because your applications, I'm running hundreds of VMs over here, and you're allocating memory but not really using them. So you can see your activeness is roughly hovering around 470 to 500 gigabytes. Now, as you can see, this value is around 50% of the DRAM capacity, 500 gig, 50% of 1 terabyte. This is a very key guideline we want to give to our customers in the context of memory tiering. One could say that your host DRAM is still too much left over. So why 50%? Well, we want to be able to absorb some of the spikes in the workload characteristics. So you have enough headroom that you can take care of these spikes. That's why we have this guideline around active memory. Now, all the results we have presented, most of the active memory for our VDI workloads, SQL Server and Oracle workloads, they were hovering around this number. Sometimes they were going up, 60% or 70 as well. But more or less, this is our key guideline around this. Another screenshot I have is for VROps. Many customers, they use this product. So since there are so many counters around it, I just want to really emphasize what exact counter to use. As I have seen the active memory on the vCenter, here I'm focusing on this counter, which is called guest active. That maps to the vCenter's active. So this is the counter. If you're using VROps, use this counter. Since active memory is one of the key guidelines we are giving, so I wanted to show an example of, okay, what if it goes above 50% DRAM? So I'm gonna use this example of Login Enterprise benchmark because over here, I'm running a lot of VMs over time. So in this case, I have EUX score on the left-hand side, which I've explained, and on the secondary y-axis, I have the number of active sessions. So these are all instant clone VMs, and every minute, 6 users log onto those VMs and starts to do these activities. As you can see over here, which is around 200 sessions, your performance starts to dip a little bit. And that is because your active memory starts to hover around this zone of 75%. Now, here, in order to cater for these spikes in the workload, your algorithm is adjusting and you see a little bit of lower performance, and then it starts to go back to normal. So this is why it's extremely important, and one of the key guidelines we are giving to our customers to monitor the active memory. The sweet spot is again around 50%. So overall, memory tiering, it helps to reduce your total cost of ownership costs. It optimizes your memory usage, and also you can have more scalability in memory allocation because you're unlocking more memory capacity using a cheaper tier. The biggest gain, obviously, improving VM consolidation ratios. You can better utilize and justify the cost of licenses. You can get up to 2x increase in memory VM density with 1:1 ratio across a variety of workloads, as we have seen in this talk. And to summarize the best practices, I cannot emphasize this enough. Key metric is active memory. The sweet spot is around 50% of the size of DRAM. And you can monitor your NVMe tier device traffic. Again, the rough guidelines are around 200 microsecond reads and 500 microseconds for writes.
Yeah, so I mean, this is a really nice feature that I think a lot of customers are going to use because it's going to allow you to be much more efficient with your servers. Thanks for coming and talking with us today, Qasim. It's great talk. I would like to say thank you to everybody for watching, and I look forward to seeing you on another episode of the Extreme Performance Series soon. Thanks, everybody.